Okay, so my presentation is on the Anomalous Payload-based network intrusion detection system. The name of this specific algorithm that we have developed is PAYL. Let's move forward. Okay, so basically, there are many intrusion detection systems available in the market. Some works on the header information of the data, some works on the payload information of the data, some are signature based that they are at the development time, they are given the signatures of all the malicious content, and at the detection time, they just compare the signature with those malicious content. And there is another one that is known as anomaly detection systems, in which there is no pre-feeded data to the algorithm, and it learns the malicious activity by the time it runs, and the more time it runs on the network, then the more it learns about the activity or behavior of the network, the true behavior of the network. So this PAYL algorithm is based on the anomaly detection system. It's a machine learning based algorithm, and it detects the malicious activity or anomaly in the network. Plus, this algorithm is based on the payload of the data, not the header information like the ports or the IP addresses of the sender or receiver. This is an unsupervised algorithm. And in testing, this algorithm has seen to achieve almost 100% accuracy with a 0.1% false positive rate for HTTP traffic. Before jumping into the algorithm, I will like to show light on some of the common attack types that can be done on networks. So one of the most common thing is exploiting the vulnerabilities that are already present in the network protocols, like in HTTP. If a user is using HTTP traffic instead of HTTPS, then there can be certain attacks that can be applied to those traffic. And there are data crawling or survey sites that scans data. They works like bot and gets the private or not so private but not publicly available data. And another thing is delivering a payload in to a vulnerable service or application. This is one of the most common type that is exploited by viruses in the computers to make their own copies and spread them in the network. This is the mechanism that was used by Stuxnet. And one of the other attack is the open port scanning. It just brute force all the open port scanning and try to find a port in which there is no password access, or the application is just directly giving the data. And another type of network attack is a denial of service attack, in which a user sends a lot of packets from one or multiple computers to a server, and that hinders the normal availability of the server to the users. So the intrusion detection system also needs to cater to such attacks and stop their access in the firewall level, so that server does not get busy with those fake requests. So what can be the consequences of the intrusions? They can compromise your all infrastructure. It can cause damage to the hardware, like in Stuxnet case, and there can be a data loss. This is one of the most bad thing, because data is more important than anything else at this point of time. Users' data privacy, financial loss, and the lawsuits that can affect the company if their system is hacked. So what's the importance of intrusion detection systems? So intrusion detection has been one of the most important topic in cybersecurity, and many organizations, that mostly financial and medical HIPAA compliant organizations, are required by law to have an intrusion detection system, commonly known as firewalls, in their networks to secure their systems. Intrusion detection, that normally known as like, people think that they can only secure the data and services, but they can also be used in forensics and in the recovery of services. If we get a report about how the intrusion happens and where the user goes and what was the payload like, then we can, by knowing the type of attack, we can recover our services better, and we can use that data in the payload if our intrusion detection system is filtering the packets, and now we know the content of the packets, and we can do forensic analysis on those data. Okay, the problem statement and related work. Basically, there are many IDS systems available in the market. Even many of them are open source and widely used. The first point I will discuss is the IDS systems that are signature based. So they, at the time of development, they are fed a database of signatures of some widely known attacks or the vulnerabilities in the network, and those IDS systems works on those signatures, and they compare all the incoming traffic with those data. So some of the examples of those systems are Snort and BRO. But now a new generation of the intrusion detection system is emerging, and it's based on the machine learning. So this new technique keeps getting the data, sensing the data from the feed, like in the local network, and it gets itself trained. First, on the training side, we train the data on some sample cases, and after the system is deployed in the wild, then this system can also keep learning at that stage as well. So it keeps getting better with time. Some of the examples of anomaly detection systems are SPADE, NIDES, and PHAD. The IDS systems, the earlier IDS systems that works on signature do not work on zero-day exploits. Zero-day exploits are the very new attacks that are not publicly known, and they can affect the system greatly. IDS does not have their signature, so they cannot protect systems from those attacks. So moving forward to the intrusion detection systems that are very related to this specific algorithm, anomaly intrusion detection system. There are many anomaly detection systems present as well, some of them as SPAD, ALAD, and PHAD, and they works on different things. Most of these anomaly detection systems work on the header information, the information like which port the request is originated, which port the request is going to, the IP addresses, the protocol, or other header values like CORS and similar headers that can be used in hacking. And these systems are able to get the header information, and they do really good job in handling the traffic in that way. But the problem is that these algorithms does not see the body of the data. Like if I am as an illegitimate owner, I send a file to another person, the file is corrupted, but the sender and receiver is legitimate, the file is malicious, the payload is malicious, then these algorithms won't mark those data packets as malicious. So the PAYL algorithm that we have built is based on the payload of the data and is very helpful in detecting this service level attacks. Okay, in the contribution section, I will first compare a little bit with a very similar algorithm to PAYL algorithm, and that is the service specific anomaly detection developed by C. Krukel, T. Toth, and E. Kerda. That algorithm does it just gets the frequency of the letters in the payload, sample them, aggregate them, and put them into 6 segments, and then do their analysis on them. So it rearranges the characters as well. So even I don't think that would be a really good idea in counting the characters and aggregating those characters and applying algorithm on them. The PAY algorithm does is that it fully it applies the algorithm on full byte distribution and based on the length of the payloads, and it uses a different distance algorithm known as Anomalous. This algorithm automatically clusters centroids that increases the accuracy, plus that allows this algorithm to be to learn in the deployment phase as well. So normally the other algorithms first train in the training side, and when they are deployed, they just work on those training data. But this algorithm keeps training itself and from more data in when it is deployed in the wild. I will discuss about it a little further in the next slides. So a basic overview of how this algorithm works. In training phase, we compute a profile of data packet that is based on the biased frequency distribution, and we measure the standard deviation of the application payload. For a single model, it works on a single host and port. Because this is not a header based, this is a payload based, so we have hard coded, or you can say fix the host and port, because we are only focused on the payload data. And after the centroid, after we have the standard deviations of the data packets, then we create a centroid model, and based on the model, we create our data clusters, and we mark their distances from the centroid. And then we deployed the algorithm into the industry, or you can say in where we have to detect the malicious activity. And in detection phase, for every data packet, we calculate the same Anomalous distance from the centroid, from the pre-computed model. And we have also specified a threshold, and if the distance is more than the threshold, then the system is going to generate a a request or something that this data is malicious and the user needs to do something about it. It will mark it as spam or similar and creates an alert. So one of the important point about the algorithm is incremental learning that I would like to explain a little more. So this developed algorithm has an incremental version in which every new model will have a little more information from the previous model. This really helps in identifying zero-day attacks and the new novel attacks that are not yet been known. And this model can be computed on the fly, hands-free, and in an automatic fashion. With time, this mechanism improves the accuracy as well as the detection of new attacks. So it makes itself better with time. The datasets used for this algorithm for testing was the 1999 DARPA IDS dataset and the This is the dataset that is publicly available on the internet. And the second dataset is the Columbia University Computer Science Department network data. The authors collected that data in the lab and consolidated the data, changed to a processing format in CSV, and then did their algorithms on this data. This data is not publicly available, but they have discussed about their results. So that is one point that I will be discussing in my comments, that there is no way to confirm the results because this data, they have not publicly publicized this data. The results of the algorithm is that it is very effective at detecting attacks. In the publicly available IDS data, among the 97 attacks, this model has successfully detected 57. And the false positive rate is also very low, that is 1%. And for specifically for port 80, the HTTP traffic, it achieves almost 100% detection rate. And in their own dataset that they have developed, they detected code red 2 malicious activity and the buffer overflow attack in that dataset. But no percentage of detection is defined in the results of the paper about this specific dataset. So coming to the presenter comments, one of the first point is that their second dataset is not publicly available and there is no way to validate their results, like what are they saying is true or not. Secondly, I think that some of the people have done their research on header-based algorithms. They have done their algorithm on the payload-based algorithm. So it would be a great thing if both these algorithms can be combined and an algorithm works on both of the header information as well as on the payload information, because both of these information contains vital data about the attack or normal behavior of the activity. So again, this is another thing that is based on only on payload. It will be better if they can work on both payload as well as the header information. The third comment I have is that in their related work section, they have only discussed the research papers that are available in that specific domain, but they have not discussed the industry products or open source intrusion detection systems, not specifically research papers, but the products that are available in the market that are also working very good. Like there is a Hoaxilla intrusion detection system that is an open source, and it is one of the very famous intrusion detection system. It can also detect anomaly in the dynamic way, just like they are doing. So they haven't discussed about these products or these already developed platforms in their related work. And there is another company called SQRL. They have their own proprietary cybersecurity automatic detection algorithms. They have open source part of it for the publicly validation. Public validation, but most of the code is private. But it also does all the things that this algorithm is doing. So it would be great if they had discussed these things in their algorithm as well. So now the discussion part.
Okay, thank you very much, Ellie. This was an excellent presentation. A quick note about your final comment. If you check the publication date of this paper, you'll find out it was published in 2004. Mm-hmm. So many of the solutions, many of the companies that you mentioned were not around at that time, or their products at least were not as well established as they are right now. However, you're right. This is one of the earlier publications on using machine learning and unsupervised learning for anomaly detection, especially the fact that they talk about incremental learning, learning over time, and enhancing the performance of the model over time is very unique. This is one of the reasons this paper has so many citations. I think it has around 1,100 citations. It inspired a lot of further research and a lot of other ideas that security data scientists have been employing in their products and their work. Now, there are many, many different things we can talk about right now. Before I dictate my own curiosities and my own thoughts, I really want to know what others think about this work and the contributions and the results obtained from this study. Anyone? Okay. This isn't really heartwarming, but let's proceed. So one of the interesting observations from the results is the fact that it does really well on HTTP traffic, port 80. Does anyone have any thoughts why the payload data from port 80 or HTTP traffic is presenting better results or staggeringly high detection rate compared to, for example, FTP port 21?
Can the presenter answer?
Sure.
Yeah, because the HTTP port sends data in the plain text and there is no encryption involved. In the FTP, the data is sent, that is not the plain text, but it's the binary format because the data transferred on FTP is of binary in nature. But in HTTP, the data is in plain text format. So it's very easy to apply algorithm on the plain text data instead of binary data for encrypted data.
That makes a lot of sense to me. I think that I also think that this is the reason they're doing so well on port 80. A quick note, I have to repeat this. I've told you about a particular thing to avoid as a security data scientist in your careers, and it's to say that your model has 100% accuracy. So in the real world, in both the scientific community and the technical community, if you say that, a lot of my colleagues and your colleagues are going to think that you either don't know how to measure accuracy or don't know, or you're lying. So how come these results are so close to 100%? Why are they getting such impressive results? What's magical about their approach? Any thoughts on this?
Yeah, maybe because the dataset already has rectified the information that this data is malicious or not, and they might have tweaked their algorithm to work 100% on the already known results.
Very well. That's an interesting idea. Where do they present the test time performance of their work anywhere in the paper?
I don't remember right now.
I actually don't remember myself. What I see here is mostly just numbers. They don't really talk about the constitution of test and training time data and the proportions. Also, we need to keep in mind that DARPA 99 was, first of all, in the year 1999. And secondly, it was it was collected from a simulated environment with very, very low degrees of complexity. Now, they also present the results of applying or deploying their model in the real world in the computer science department's network at Columbia University. And they mentioned that the model was able to detect, I believe, was it called Red? Was it NIMDA? I think it was one of the better known malwares of that time, 2003, 2004. But they do not have an accurate count of number of intrusions or number of malicious traffic packets. So presenting their results in this form can be misleading. It's not very scientifically accepted in this day and age when everyone knows about the basics of machine learning and they know that machine learning models in the complex world can't come close to 100% accuracy. However, there are still interesting observations that can be made. There's another idea that I want to put up for discussion, and it's the fact that they look at the distribution of payload data for port 22 for SSH. And SSH data is by definition encrypted. Why should they be able to infer anything useful from encrypted data?
I don't think you can get much from encrypted data because by a single bit change, the data changes drastically. So there is no specific sequence in it.
Sure. How about the size of the encrypted packets?
That is a good point, but many legitimate data is going to have, like, even 99% of legitimate data is going to have the size of the 1% malicious content.
Yes, that's a good point. So I'm still not very sure about the honesty or at least the accuracy of the results the paper presents, because obtaining useful information from encrypted packets on the SSH channel, especially with their approach to featureization, which is essentially n-grams, is very, very unlikely to result in any significant information content. But again, the good thing is Sai is talking about the fact that they have not released the dataset. However, DARPA 99 is available. It's open source. We can go ahead and download it whenever we want. And implementing this model is also very simple. So it can be straightforward for us to verify to some degree their findings. Has anyone done that? I don't know. I doubt it. It's rare that researchers spend their time on verifying the findings of a paper instead of coming up with their own results. But it can be a worthwhile endeavor to just implement this model. We already have all of the parameters that we need to some degree to replicate this model and train it on DARPA 99 and see how well it does. Just a seed idea. Okay, any other thoughts, any other comments? Ali, did you learn anything useful from this paper?
The network intrusion detection system internal mechanism.
Very good, yes. So one of the important takeaways of this paper is to learn about some of the statistical or data scientific techniques applied to intrusion detection. especially when it comes to unsupervised learning and anomaly detection.
Yeah. But see, I have a concern here as well. The same concern that you had, that that their algorithm works on unencrypted data. But right now, you can say most of the traffic is encrypted in the form of HTTPS or in the form of SSH or things like that. So this intrusion detection system won't be of any use in the wild right now. So
That's correct. Yes, that's a good
how,
observation.
yes, so how we can tweak the system to work in the current environment, like making the system with encrypted data, like making such intrusion detection system with encrypted data might be a good project, I think.
I agree. Now, I want to add to that and point to the fact that this model is not taking the temporal information into account. There is useful information in the time domain representation of network traffic,
Mhm.
right? Looking at whether a particular user has been sending large HTTP packets or ping packets to the server in sequence can help us a lot in detecting particular denial of service attacks, or looking at the sequence of requests coming from the user, a particular user or a particular IP address, can help us gain a better insight into the context and the objective of those requests. This model does not take temporality into account. And that's one of the things that many other research projects that build on this try to account for, try to implement in their own models. However, believe it or not, to this day, in the day of deep learning, looking at sequential data in network traffic and trying to come up with anomaly detection models accordingly is still an open problem. There are some proof of concept implementations and proof of concept architectures that have proved somewhat useful in limited and constrained circumstances, but very few apply in general. One of the problems that Matt, Luke, and their team who are working on deep learning based anomaly detection for intrusion detection systems are dealing with at the moment is the fact that sequential models do not fare well with multidimensional input representations. That's just something to think about if you want to get into hardcore data science research for cybersecurity.
Uh, yeah, I would like to mention one point here. Recently, I was working on how the Kaspersky antivirus works, like on the encrypted traffic. So as the antivirus does not know what the encrypted traffic has and how its firewall is working. So the way they are doing this is that they install a virtual network adapter on your computer when you install the antivirus, and they also install their own certificate on your computer. So whenever you open facebook.com, the certificate in your browser is not of Facebook, it's of Kaspersky. So whenever the data transfers from your computer, it first goes to the Kaspersky virtual adapter, they decrypt the data, then they do their analysis, then it encrypt the data again with the real Facebook certificate, and then it sends it to the Facebook. So it works at man in the middle and decrypts the data.
Yeah, so that's essentially a man in the middle attack, but
Yes.
it's being implemented for uh, useful and humanitarian purposes. It's actually very common in IDS IPS solutions to implement such a solution where an intermediary node is added to decrypt, analyze, and re-encrypt publicly encrypted data packets. But what about data packets that are end-to-end encrypted and you do not have access to the private key to decrypt it? What if there is a bot botnet client installed on your computer, and it's transmitting fully encrypted data, and you do not have access to the public key and the private key to decrypt it. A solution approach to these problems is called traffic analysis. Traffic analysis is a subfield of cybersecurity, or in general, communication security, that intends or aims to solve the problem of understanding encrypted traffic. So, for example, back in the days of World War II, when Germans used fully encrypted communication techniques, the Allied forces looked at the timings of the transmissions of messages and the density and volume of traffic being generated from different sources to anticipate attacks. The same techniques are now being applied to do traffic analysis in Tor networks, or even further in encrypted communications between criminal organizations and terrorist networks. There's a lot to talk about here. Unfortunately, we are 10 minutes past our end of class, so we have to end the discussion here. Ali, thank you so very much for this excellent presentation.